Today's lecture we are going to continue talking about the wind energy. In this section we are going to continue talking about the effect of tower height and the impact of tower height on the wind energy production. The need for a taller tower. One way to get the turbine into a higher wind to increase its power is to mount it on a taller tower. In the first few hundred meters above the ground, wind speed is greatly affected by the friction that the air experiences as it moves across the Earth's surface. To characterize the impact of the Earth's surface roughness on the wind speed, so we are going to apply this formula. V over V naught equals H over H naught to the power alpha. What is V? The wind speed at height H. What is V naught? The wind speed at height H naught. And H naught, it's often a reference height of 10 meters. And finally, alpha is the friction coefficient called Hillman or shear exponent. So this table shows the friction coefficient or shear exponent for various terrain. So this is the terrain characteristics and this is the friction coefficient alpha. In case of smooth, hard ground or calm water, you end up with coefficient alpha equals 0.1. In case of tall grass on level ground, the alpha 0.15. High crop hedges and shrubs, alpha equals 0.2. Wooden countryside, many trees, alpha 0.25. Small town with trees and shrubs, alpha equals 0.3. And finally, large city with tall buildings, alpha 0.4. So according to your situation, you have to select the right friction coefficient alpha, and then you can apply this formula to get the right wind speed at that height. So while the power law given in the previous equation 5 is very often used in the United States, there is another approach that is more common in Europe. This alternative formulation is V over V naught equals ln H over L over ln H naught over L. So what is L? The roughness length. So the relative power of the wind at height H versus the power at the reference height of H naught, P over P naught equals at the end V over V naught to the power 3 or H over H naught to the power 3 alpha. So if you are in the United States, you have to use this formula. If you are in Europe, you have to use this formula. And then you can calculate the relative power of the wind at height H versus the power at the reference H naught from this formula. This table shows, according to Europe, you have the roughness length L. So this shows the roughness length L for different terrain. And there is a roughness class from 0 to 4, 5 different classes: water surface, open areas, farmland, urban districts, and dense urban. And you have different length values, ranges from almost 0 up to 1.6. This two figures shows the wind speed and power ratio versus height. So what will happen to the wind speed and the power ratio when the height increases? When the height increases, the wind speed increases with this rate, and the power ratio increases with this rate. And these graphs have been plotted for different alpha values. Alpha from 0.1 to 0.3 values. So let's take this example. A wind turbine with a 50-meter rotor diameter is to be mounted on either a 50-meter tower or 80-meter tower. Assume that the usual 1/7 rule of thumb for the shear friction coefficient alpha, you have to choose alpha equal 1/7. First of all, we need to compare the wind power density at each hub height. Then for each height, compare the ratio of the power density at the highest point that the tip of the rotor blade reaches to the lowest point to which it falls. To solve this problem, first of all, we need to compare the wind power density at each hub height. So we have 50 rotor diameter installed on 50-meter tower and 50-meter rotor installed on 80-meter tower. So then we are going to use this formula, P over P naught equal V over V naught cube, or H over H naught to the power 3 over alpha. 3 over 3 alpha. So alpha is given, so we can apply H over H naught to the power 3 alpha. So P over P naught equals, what will be the value of H? First one, 80. What will be the value of H? The second one is 50. So 80 over 50 to the power 3 times alpha. And alpha is given 1/7. So you end up with 1.22. That means 22 more power available at the taller hub height. The second part, for a 50-meter blade at a 50-meter hub height, the tip reaches to 50 plus 25, so the tip reaches to 75 meters at its highest point, and 50 minus 25, you get 25 meters at its lowest. So when you apply this, the highest, or we call it the tip of the rotor blade, the highest point that the tip of the rotor blade reaches to the lowest point at which it falls. That means it reaches to the highest point will be 75 meters and the lowest point will be 25 meters. When you divide them together to the power 3 alpha, you will get 1.6. That means the power in the wind at the top of the rotor swing is 60% higher than that when the tip reaches to the lowest point. This is for the 50-meter hub. What about the 80-meter hub? For 80-meter hub, 50 plus 40, 80 plus 25, you get 105. And 80 minus 25, you get 55. So 105 over 55 to the power 3 alpha, you get 1.332. That means 32%. The power in the wind at the top of the rotor swing is 32% higher than it when the tip reaches its lowest point. In this section, we're going to talk about the wind turbine power curves. We start with the bits limit. For the heat engines, like this, the Carnot efficiency limits the maximum work that can obtain from an engine working between the hot and cold reservoir. If you study the heat engines, you are going to you are going to see or hear about the Carnot efficiency. For photovoltaics, the material band gap will limit the conversion efficiency from sunlight into electrical energy. In for fuel cells, the Gibbs free energy will limit the energy conversion from chemical to electrical form. So in these different systems, there is some kind of efficiency that will limit the conversion from one type to another. The same thing happen here in wind turbines. So now we are going to see the constraint that will limit the converting the kinetic energy in the wind to mechanical power. This is called Pitt's limit. So it is interesting to note that the number of energy technologies have certain fundamental constraints that restrict the maximum possible conversion efficiency from one form of the energy to another. Here we will explore the constraint that will limit the ability of a wind turbine to convert the kinetic energy in the wind to the mechanical power. The original deviation or derivation for the maximum power that a turbine can extract from the wind is credited to a German scientist called Albert Pitts. The analysis begins by imagining what must happen to the wind as it passes through wind turbine. This figure shows that the wind leaving the turbine has a lower velocity and its pressure is reduced, causing the air to expand downwind of the machine. What Pitts showed was that an ideal wind turbine would slow the wind to 1/3 of its original speed. This is the upwind V, and this is the wind at the turbine itself VB, with the rotor area A, and the downwind after the wind turbine will have the velocity Vd. So now we have three different velocities, V, VB, Vd. So the power extracted by the blades BB is equal to the difference in kinetic energy between the upwind and downwind airflows. That means BB equals half M prime, or the derivative of M, first derivative of M, V squared minus Vd squared. M prime or M dot here equals the mass flow rate, which is rho A VB. The ratio of the downstream to upstream wind speed is lambda equal Vd over V. Then we end up with BB half rho A V squared minus, we are going to replace lambda here, Vd over V by lambda, so end up with lambda squared V squared times V plus lambda V over 2. So we are going to separate this in two different quantities. The first one equals half rho AVQ, and this we'll call it power in the wind, multiplied by another factor half 1 plus lambda times 1 minus lambda squared. This becomes a fraction extracted, and this will become the efficiency. The power extracted from the wind equal to the upstream power in the wind multiplied by the quantity in brackets, which is the efficiency of the rotor. So we call half 1 plus lambda times 1 minus lambda squared by Cp. Cp is the rotor efficiency. Then, to find the maximum possible rotor efficiency, we simply take the derivative of the equation. Okay, we need the maximum efficiency, so we take the derivative of this equation number 9 with respect to lambda and set its equality to 0. So dCb by d lambda, and C equalize it with E0, you end up with lambda equal third, one third. One third, or VD over V equal one third. That means the maximum rotor efficiency will become 59.3%, does not exceed 60%. And this figure shows the blade efficiency CB with respect to the ratio VD over V or lambda. So this will happen at lambda equal third, one third. The maximum efficiency will be not exceeding 60%, exactly 59.3%. So the efficiency in extracting the wind power, Bates limit and the power coefficients here. The power coefficient CP is the ratio of the power extracted by the turbine to the total contained in the wind resource. Or CP, we can call it PT over PW. Okay, PT is the power extracted from the turbine to the wind power, or turbine power divided by wind power. This is the power coefficient. The turbine power PT is half rho AV cube times CP. The Bates limit is the maximum possible CP, which is 16 over 27 or 59% almost. 59% efficiency is the best conventional wind turbine can do in extracting power from the wind. Here we'll talk about the power sensitivity to the wind speed. Wind speed in meter per second, or in different units like kilometer per hour or mile per hour, changes from 2.5, 5, 7.5, 10, 15, 20, 30, 40. What will happen to the power density? Power density, we can, the units for power density is kilowatt per meter squared or horsepower per foot squared. So we take kilowatt per meter squared. So when the wind speed 2.5 meter per second, almost the power density is 0. But when it increases to 5, it increases 8 times. Which when the wind speed increases to 7.5, it reaches to 0.27. And when it increases by small values, the power increases too much, because it depends on the cube of the velocity. Tip speed ratio, TSR. What is TSR, or tip speed ratio? Is the ratio of the speed of the windmill rotor tip at the diameter d in meters when rotating at the omega revolution per minute RPM to the speed of the wind v meter per second, and it is numerically TSR, the rotor tip speed over wind speed. Rotor tip speed is RPM times by d over 60 divided by wind speed is v. When the windmill rotor is stationary, its tip speed is also 0, and the rotor is called stalled. This occurs when the torque T produced by the wind is below the level needed to overcome the resistance of the rotor. So here, this graph shows the rotor efficiency for different rotor types. This is the rotor efficiency in percentage, and this is the tip speed ratio, TSR. For different types of turbines, like American multi-blades, modern 3-blade, Darius rotor, high-speed 2-blade, and so on. We can see that the rotor with fewer blades reach their optimum efficiency at higher rotational speeds. You see here, multi-blade, it reaches to its maximum value at small tip speed ratio. But if you wanna, but for fewer blades, they reach to the maximum efficiency, like here and here and here and here, at higher tip speed ratio. And the maximum will not exceed the beats limit, as we mentioned before. In this section, we are going to talk about the idealized wind turbine power curves. So the idealized wind turbine power curve is going to be delivered to you by the manufacturer. This shows the relationship between the wind speed and electrical power expected from the wind turbine, including blades, gearbox, and generator. This is the wind turbine, or the power delivered from the wind turbine versus the wind speed. What will happen to the idealized power curve? Below VC, VC is the cut-in wind speed. Below VC, what will happen? Cut-in wind speed VC is the minimum needed wind speed to generate net power. Since no power is generated at wind speed below VC, the portion of the wind's energy is wasted. Then after VC, you are going to collect power or deliver power from the wind turbine when the wind speed increases more than VC, until you reach to VR. What is VR? VR is rated wind speed. Rated wind speed is the wind. When the winds reach to the rated wind power, the generator delivers as maximum power as it is designed for. Above VR, there must be some way to shed some of the wind's power, or else generator may be damaged. After the wind speed increases more than VR and reaches to VF, VF is called furling or cut out wind speed. Cut out or furling wind speed, at some point the wind is so strong that there is a real damage to the wind turbine. At this wind speed VF, the machine must be shut off or shut down. Above VF, mechanical brakes lock the rotor shaft in place and the output power is zero. In this part, we're going to talk about the real power curve. The real power curve, actually, we are going to see this is the power delivered versus wind speed, and this is for this curve for small diameter wind turbine, and this for large diameter wind turbine. What will happen for large diameter? They reach to the maximum power or maximum power delivered at lower wind speeds. So increasing rotor diameter reduces the rated wind speed, emphasizing lower speed winds. If you have same diameter, but one with the smaller generator and one with the larger generator, so what will happen? Increasing the generator size increases the rated power, emphasizing the higher wind speed. These are the actual power curves for the wind turbine. This is for Vestas V42 600 over 42, and this is for NIG Mekon 1000 over 54, and the third one with the higher power delivered for NIG Mekon 1500 over 64. What are those three types? For example, the first one, VR 600 over 42, this type of wind turbine producing 600 kilowatt and the rotor diameter is 42 meters. For the second one, NIG Mekon, this is producing rated power of 1000 kilowatt and the rotor diameter 54 meters. Third one with the biggest rotor diameter 64 meter, it produces the rated power of 1500 kilowatt. This example, we are going to discuss, we'll see how to apply the previous information to solve this example. So we have a diameter 40 meter, three bladed wind turbine produces power 600 kilowatt at a wind speed v 14 meter per second. Air density is the standard 1.225 kilogram per meter cube. Under these conditions, at what RPM does the rotor turn when it operates with the TSR of 4? Then what's the tip speed ratio? Or the tip speed of the rotor. The tip speed ratio is given. What is the tip speed of the rotor? And then if the generator needs to turn at omega 1800 RPM, what gear ratio is needed to match the rotor speed to the generator speed? And finally, what is the efficiency of the complete wind turbine, including the blades, gearbox, generator under these conditions? First of all, we are going to use the formula for TSR, tip speed ratio. It's the rotor tip speed over wind speed. How to calculate the rotor tip speed? RPM by D over 60. And the wind speed is V. V is given. And we need to calculate RPM by is constant, D is given. So the only unknown, TSR is given, so the only unknown is RPM. Then to calculate the tip speed of the rotor, tip speed of the rotor is RPM multiplied by pi D over 60. So let's see this. Once we calculate this, to calculate the power, it's half rho AV cube. This is the power in the wind. First of all, RPM is TSR 60V over pi D. So everything is known, 6, 4, 60, 14 over pi 40. You get 26.7 revolution per minute. Once we know RPM, now here we say that that's about 2.2 seconds per revolution. It's pretty slow. So the tip speed becomes this RPM by D over 60, you get 55.9 meter per second. Notice that even though 2.2 seconds per revolution sounds slow, the tip of the blade is moving at a rapid 55.9 meter per second or 125 miles per hour. So it looks slow, but the blade itself has a high speed. If the generator needs to spin 1800 RPM, then a gearbox is needed, and the nacelle must increase the rotor shaft speed by a factor of, so you have 1800 RPM, and the rotor RPM from here, part A is 26.7. So the conversion ratio of the gear ratio becomes 1800 over 26.7, you get 67.4. This is a gear ratio. Then the power from the wind, half rho AV cube. So it's half rho 1.225 A, the area. So it's area by A squared or by D over 4. So by over 4 D squared, and D is 40, times V cube, the speed of the wind cube, 14 cube, you end up with 2112 kilowatt. This is the power in the wind. Once you have the power in the wind, so the overall efficiency of the wind turbine is the 600. This is the produced power. So the produced power divided by the total power of the wind. So 600 divided by 2,112 kilowatt, you end up with 0.284 or 28.4. This is the overall efficiency. So notice that if the rotor itself about 43 efficient, so due to the using the gearbox, so the efficiency will be dropped from 43% up to 28.4%. So the gearbox, then the efficiency of the gearbox times the efficiency of the generator would be about 66%. 43% times 66%, you end up with 28.4. So the efficiency of the gearbox and generator becomes 66%. So the overall efficiency does not exceed 29%. So another example, an 82 meter 1.65 megawatt fixed speed wind turbine has a rated wind speed of 13 meters per second. It is connected through a gearbox of 4-pole 60 Hz synchronous generator. We need to calculate the gear ratio should the gearbox have if the turbine is designed to turn at 14.4 RPM. What is the tip speed ratio when the winds are blowing at the rated wind speed? What is the overall efficiency of the machine at its rated wind speed? And the power curve for this machine indicates that it will deliver half of its rated output in 8 meters per second wind. What is the efficiency and TSR at that wind speed? Finally, what would be the TSR with 8 meters per second wind if the generator could switch from 4-pole to 6-pole? How to solve this example? First of all, we are going to use this formula for the type of synchronous generator. Depending on the number of poles, we can calculate the speed. So the speed, the generator shaft spins at a speed of 120 F over P. 120 times F. What is F? The frequency of the synchronous machine. So frequency is 60 over the number of poles. If you have 4 poles, so you end up with 1,800 RPM. Once you have 1,800 RPM, so you can find the gear ratio. The gear ratio will be the generator speed over the rotor speed. The generator speed, we calculated already 1,800 RPM over the rotor speed. It's given in the example 14.4 RPM. You end up with 125 gear ratio. This is the part A. Part B, we need to calculate the TSR at 13 meters per second. So TSR is, as we mentioned before, from this equation, TSR is the RPM by D over 60V. Okay, so RPM, what is RPM here? RPM is given 14.4 times by D over 60V. So V is given, D is given, and RPM is given, so the TSR is 4.76. The overall efficiency at rated wind speed, first of all, we need to calculate the power, the wind power, from the formula half rho A V cube. Half rho is known as a constant, A, the area, pi over 4D squared, times the wind velocity cube, 13 cube, you end up with 7,106 times 10 to the power 3 watt. This is the wind power. So the overall efficiency of this 1.65 megawatt machine, you have to divide 1.65 megawatt over 7.1 megawatt, you end up with 23.2%. For the next requirement, efficiency and TSR at 8 meter per second. So first of all, we calculate the power of the wind, half rho A V cube. The new V cube will give you the new power. Once you have the new power, you can calculate the new overall efficiency. It's 49.8%. And the TSR from this equation at 8, the new speed of the wind, 8 meters per second, you get the new TSR. Switching from 4 pole to 6 pole will change the number of revolutions to instead of 1,800 to 1,200. Then with our 125 gear ratio, the rotor speed will be 1,200 RPM over this gear ratio, you'll get 9.6 RPM. So with this 96.6 RPM, we need to calculate the new TSR, will be 5.1, and this looks closer to the optimum range of TSR values. This is the end of this example. This section, we are going to present the IEC wind turbine classification. These are some kind of practical wind turbines, and this table shows the classification of wind turbine in terms of its wind: high wind class I, medium wind class II, and low wind class III. And for each wind turbine class, generator class, we have the average wind speed at hub height, the 50-year maximum 10-minute wind speed, 50-year extreme 3-second gusts, and the turbulence of class A, class B, class C percentage. The turbulence intensity is the ratio of the standard deviation of the wind speed to the 10-minute mean wind speed. And we can see that for high wind, that means class I, the first class, the average wind speed is highest, and also the V reference and VE50 is the highest ones, while the turbulence is selected to be fixed for all three classes. IEC stands for the International Electrotechnical Commission. These are some kind of power curves and calculate efficiency. This is efficiency, and this is efficiency for this type of turbine Vestas V82 1.65 SCIG. SCIG stands for the squirrel cage induction generator. This for the power, and this for the power, rated power, and this for the efficiency versus wind speed. And we can see the rated power is 600 kilowatt and the diameter is 42 meters. For the other type of wind turbine, it's called GE 2.5103 PMSG. PMSG stands for the permanent magnetic synchronous generator. And this curve for power, and this curve for the maximum efficiency versus wind speed, with the rated power 2500 kilowatt and the rotor diameter 103 meter. Now the question is how to measure the wind. Measuring the wind, there are three types of anemometers. The first one is called Cup anemometer. The second one is the sonic anemometer, and the third one is SODAR. SODAR is the ground-mounted sonic detection and ranging. Anemometers uses pulses of sound waves. It calculates horizontal and vertical wind speeds as well as the direction. There is another type called LIDAR. LIDAR is the light detection and ranging system, are similar but use light instead of sound. The last section of this lecture, we are going to talk about the average wind speed and the average power in the wind. We can begin to explore this important nonlinear characteristics of the wind by rewriting the equation in terms of the average value. Why average? Because you don't have fixed or constant speed all the time or the day or across the year. So you have these values are changing, so you have to calculate the average speed and the average power. In other words, we need to find the average value of the cube of the velocity. To do so, we will require that we introduce some statistics. How to calculate the average wind speed? The average wind speed can be thought of as a total meters, kilometers, or miles of wind that have blown past the site, divided by the total time that it took to do so. Suppose, for example, that during the 10-hour period, there were 3 hours of no wind, 3 hours of 5 mile per hour wind, and 4 hours at 10 mile per hour wind. The average wind speed becomes 3 times 0 plus 3 times 5 plus 4 times 10 over the total number of hours. 3 plus 3 plus 4 is 10. So you get 55 over 10, you get 5.5 meter per hour. This is the average velocity or wind speed. Here, this histogram, discrete wind histogram, shows at different wind speeds and these are the hours per year in wind speed. And for example, 0 wind speed happens 24 hours a year. 1 wind speed, 1 meter per second wind speed happens 276 hours per year. And then you have to collect all these wind speeds from 0 to the maximum speed 25 meter per hour and the number of hours per year, and then the total number of hours, you are getting the number of hours per year, which is 8,760. And this is the distribution, how it looks like, the number of hours per year wind speed versus the wind speed. This example actually will show you how to use this data. Using the data given, find the average wind speed and the average power in the wind, watt per meter squared. Assume that the standard air velocity is 1.225 kg per meter cube. Compare the results with that which would be obtained if the average power were miscalculated using just the average wind speed. So we need to set up a spreadsheet to determine the average wind speed V and the average value of the V cube. Let's do a sample calculation of one line of a spreadsheet using the 805 hour per year at 8 meter per second. So we'll take only 8 meter per second like this in the table. At 8 meter per second, first we need to calculate the fraction of annual hours at 8 meter per second. So from here, 8 meter per second, the fraction of hours per year is 805 hours per year, divided by the total number of hours per day, 24 times the total number of days per year, 365. So you get this fraction of annual hours at 8 meter per second, 0.0919. So V at 8 meter per second, we have to multiply it by the fraction of the hours. So V8 becomes 8 times the fraction, you get 0.735. Then you get V8 cube times the fraction. So 8 cube times the fraction, you get 47.05. So the rest of the spreadsheet is to determine the average wind speed using the equation, so it will follow the same principle. First you have to find the speed, the hours per year, the fraction of hours at that velocity, and then calculate the velocity times the fraction and the cube of the velocity and the cube of the velocity times the fraction. So this is the cube, the velocity times the fraction, the total will be 7. And the cube of the velocity times the fraction you get with this total number 653.24. This is what you are going to use in your calculation. So the average speed is 7, but the cube of the velocity, average cube of the velocity becomes 653.4. So B average becomes half rho V cube average. So you are going to use this number in your calculation, multiplied by rho, multiplied by half, you get 400 watt per meter square. This is the right answer for the average power. But what will happen if you are going to miscalculate the average power using only 7? So this is the wrong calculation. Half rho V average cube. So if you take 7 and you make it cube and multiply by rho half, you get 210 watt per meter squared. This is the wrong answer, but you have to follow this to find the right answer. Wind power calculation, wind power classification. Actually, this standard wind power classification from classes 1 to 7 with the average power speed, average wind speed at 10, average wind speed at 50, wind power density at 50, average wind speed at 80, wind power density at 80, and so on. And these are different distribution of these classes. Classes can be 1, 2, 3, 4, 5, 6, 7 can be calculated or can be used in this map in the United States. This is the end actually of our lecture today. Thank you.